In the chem activity number 14 and the corresponding videos, we'll be continuing our discussion of the theoretical justification for the relative acidity, basicity of various molecules and ions. In particular, we're focusing on the stability of the negatively charged conjugate base, and we're looking at what factors will stabilize that negative charge. So far, we've looked at the atom effect as well as stabilization by resonance. The two last factors that we need to consider is the inductive effect, or stabilization by induction, and as we will see, it's also possible to have destabilization by induction, as well as the orbital effect. So let's turn our attention to some data that helps illustrate what happens in terms of the inductive effect. So I'm looking at teaching model number 1, and you can see that we have a series of carboxylic acids. There's an increasing acidity going down the chart, as we can see the pKa gets smaller and smaller for each of these acids. What changes is that there are more and more chloro groups on the carbon number 2. As before, our focus will be on the relative stability of the conjugate base. And again, the more stable is the conjugate base, the more acidic will be the corresponding conjugate acid. Now, carboxylic acids, in terms of organic molecules, are actually relatively acidic because they produce a conjugate base with a good atom effect in that the negative charge is on oxygens, and secondly, there's always stabilization by resonance. So if we look at our first conjugate base, I'm going to draw in the resonance form. This shows the delocalization of electrons and the fact that the negative charge sits on both of the oxygens. I can draw in the same resonance form for all the other conjugate bases. So we can say that all of the conjugate bases are stabilized by resonance. And in turn, this impacts the atom effect in that all of these have negative charges on oxygens, and in particular, 2 oxygens. So far, everything is the same in terms of these different conjugate bases. Clearly, though, the conjugate base at the bottom of the table is the most stable, and therefore we need to introduce this idea of the inductive effect. Induction is the pulling of electron density along the sigma bonds because of a difference in electronegativity. Now, the inductive effect doesn't always stabilize, but in terms of a negative charge, if there is an electronegative group near that negative charge, the electronegative group can pull electron density along the sigma bonds and thereby reduce, in a sense, the electron density about that negative charge. So for instance, in our second conjugate base, corresponding to the acid with a pKa of 2.87, we can draw bond dipoles in a sense like this, showing that electron density is being pulled towards that chlorine. And in a similar fashion, we can do that for the other conjugate bases. And as you might imagine, the more electron withdrawing groups that we have, like the electronegative chlorine, the greater will be this inductive effect. And indeed, this would be a stabilizing effect in this particular case. One of the ways that we could show that in our chart is that we can show increasing amount of stabilization by induction going down the chart. Now, one of the things that perhaps you might have noticed is actually even the carboxylate here without the chloro group has some stabilization by induction, because in addition to the resonance, there's also the pulling of electron density along the sigma bonds. So it would actually be correct to put a tick here that is in the first column for stabilization by induction. But now I'm going to put an extra tick here, an extra tick here, and an extra tick here to show that that effect gets more and more extreme going down the chart. Now, when we come up with a concluding statement, it is helpful to be able to refer to the different conjugate bases and to the different conjugate acids. Rather than have to call them by name, I think it's helpful on the left-hand part of this chart is to simply refer to them either by regular Arabic numbers or Roman numeral numbers so that we can easily identify which conjugate acid and which conjugate base we're talking about. If we want to summarize these ideas in a concluding statement, it might look something like this. All the conjugate bases have the same atom effect, O negative and O negative, and they also all have stabilization by resonance. But it is conjugate base 4 that's the most stable because it has, and I use the word hyper here, stabilization by induction. That's kind of my own terminology, but I think you get the idea. It has extreme stabilization by induction, and that's because it has 3 electron withdrawing chloro groups versus 2 versus 1 and then versus none. Therefore, we would conclude conjugate acid 4 is the strongest acid. Again, I hope you get the sense of the pattern. You talk about the stability of the negatively charged species, and then you make a conclusion about the corresponding conjugate acid. So we've introduced this idea of stabilization by induction, and one of the things that you've noticed from this trend is that the more electron withdrawing groups we have, the greater will be the effect of stabilization by induction, or actually any inductive effect, whether it be stabilizing or not. We need to explore a little bit further, however, the inductive effect, and this is illustrated in the next chart. So here we're comparing, once again, the relative acidity of 2 carboxylic acids. But in one case, we have a chloro group attached, and in the other case, we have a bromo group attached. So let us do an analysis and make a prediction about which particular acid will be stronger. I'm going to leave it to you, first of all, to complete this chart, and then let's discuss it together. So there are several spots where we can start. One, I can identify the different conjugate acids and conjugate bases. If you're asked to, you should draw in the corresponding resonance form. So I'm going to do that right here. And of course, both of them have a corresponding resonance form. I can start to make some conclusions that both of these have the same atom effect. So O negative, O negative, O negative, and O negative. And both of them have stabilization by resonance. And I can't really say that one is better than the other. What about stabilization by induction? So again, there's electron density being pulled along the sigma bonds away from the negative charge. This helps reduce the electron density about that negative charge. As you might imagine, the more electronegative atom is better at pulling electron density through the sigma bonds. So I would argue, therefore, that this conjugate base number 1 would be more stabilized. I can put that as a conclusion in the following way. Both conjugate bases have the same atom effect, O negative and O negative, and have stabilization by resonance. But it's conjugate base 1 that's the most stable because it has better stabilization by induction. So in a sense, what I'm doing here is I'm summarizing as much as possible all the things that are in the chart. And I state here chlorine is more, and then remember that that X represents electronegative. Therefore, conjugate acid 1 is the strongest acid. And notably, I didn't actually put my tick marks into my chart, so I better do that. So I would put 2 tick marks, let's say for the stabilization by induction by the chloro group, and I would put 1 tick mark for the stabilization by induction for the bromo group. Now I also acknowledge that there is, of course, stabilization by induction already because of what's going on about the carboxylate. Again, these tick marks are not meant to be completely quantitative. It's just acknowledging that there's a greater effect in the conjugate base 1. So far we've seen that the more electron withdrawing groups will result in a greater inductive effect, and the more electronegative withdrawing group will result in a greater inductive effect. There's one other feature that we need to look at in terms of the inductive effect, and this often leads to some confusion for students. So let's take a look. So here I'm looking at teaching model number 2, and we're looking at the relative acidity of the hydrogens on 1-fluoropropane. Now in this particular example, we have only 1 fluoro group, but actually we have multiple hydrogens that could come off. So you can see that in the row number 1, I'm assuming that it's this hydrogen right here that I've just drawn in that has come off, that's been donated. Alternatively, it could be the hydrogen on one carbon away from the fluorine. Finally, it could be the hydrogen right next to the fluorine that could be removed. Now you're asked to consider, or at least make a prediction, about what would be the pKa's for each of these protons. So in key question number 3, I make the statement the values for the pKa's for the 3 different possible conjugate bases are 40, 36, and 29. Now as I'm looking at this, I think that there's a misprint there, and I ask you to change. It should be the values for the pKa's for 3 different possible conjugate acids are 40, 36, and 29, because of course it's an acid that has a pKa. So write the value of the pKa in the appropriate location of the table in teaching model number 2, and then be prepared to justify your prediction. You may want to stop the video, make your prediction, and then continue. So here are the pKa's. Now many students actually would give the pKa for, and I'm going to label this as number 1, 2, and 3. They would have given the pKa for my conjugate acid number 1 the lower pKa. And the argument is, when the conjugate base forms, then with the fluoro group being so far away, the negative charge is really spread out. But one of the reasons why I share this data with you is to point out that the inductive effect is a short range effect. So let's make that note right here. So the inductive effect is a short range effect. And therefore, in order for the negative charge to be stabilized, it's best if that negative charge is as close as possible to the electron withdrawing group. This sort of effect does not apply to looking at resonance, where you can get delocalization of electron density through an entire molecule. But in this particular case, it's this negative charge right down here that's right next to the fluoro group that really feels the effect of the electron density being pulled towards that fluorine. Now, to some degree, the negative charge here on that carbon is feeling something of an effect, even though it's several carbons away, because we know that a typical alkane has a pK of around 50. So in this case, this conjugate base is somewhat stabilized, and the corresponding conjugate acid is definitely stronger. But certainly keep in mind that the inductive effect is a short range effect. We can add a summary statement then. All the conjugate bases have the same atom effect, so clearly the negative charge is on carbons throughout. There is no stabilization by resonance in this case. But the conjugate base 3 is the most stable because it has better stabilization by induction. And this is because the carbon is closest to the electron withdrawing group of fluorine. Therefore, we would argue that the conjugate acid 3 is the strongest acid. So we've essentially summarized the main points concerning the inductive effect. Number 1, the more electron withdrawing groups will be more stabilizing of the negative charge. The more electronegative the atom is, the more stabilizing it is of the negative charge. And the closer the electron withdrawing group is, the more stabilizing of the negative charge. Now, I want to mention one other effect here that sometimes I see students get confused about. So I'm going to draw yet another conjugate base, which corresponds to a completely different conjugate acid. And so I'm going to put the bromo group in here and the negative charge. Now, sometimes students make the argument that the conjugate base that I just drew here is even more stable than the conjugate base involving the fluoro group. And the argument they use is they say, well, the bromo group is much bigger, and therefore it can distribute the charge better. But remember that what we're looking at here is the ability of an atom to pull electron density along the sigma bonds. And this has to do with electronegativity. It has nothing to do with the size of the atom. Where size is important is when we're talking about the atom effect and we're comparing different atoms up and down the periodic table. So the structure that I just drew is not more stable than the structure that involves the negative charge next to the fluoral group. The fluoral group is, of course, more electronegative than the bromo group.